Hello and welcome to this live talk on radar system design with MATLAB and Simulink. My name is Abderrahim Belissaoui and I'm a senior application engineer at CS, part of the CS technical team. In this talk, I'll be walking you through different MATLAB and Simulink features for designing and simulating radar, as well as deploying to production. I will talk about radar design and simulation with MATLAB and Simulink. A little bit more about myself. I have background in radar, communication, and signal processing. At CS, the exclusive partner of Mathworks, I focus on radar and communication areas and application. And today I'm excited to walk you through different features that MATLAB and Simulink have for radar system design. Our agenda for today is going to start with Radar Toolbox's applications. Then we're going to dive deeper into radar system engineering, radar scenario and data synthesis, and then multifunction and cognitive radar design with MATLAB and Simulink. Let's start with giving an overview of what is actually a radar system. So a radar system is composed of an antenna and RF front end followed by a signal processing components, data processing block, and for multifunction radar, we have a resource manager and control center. Designing them or designing radar systems in MATLAB is supported from requirements to deployments. But within the software, you need to implement the environment as well, and that include scenes and scenarios. Once you have the radar design modeled in MATLAB and Simulink, you can put it in a scenario and simulate the correctness of your design and the algorithms for radar. This process of designing and simulating radar is iterative. As I said, it starts with requirements and ends with deployment. And it's based on a artifacts or a digital artifact. This model or this radar model can be used for analysis, simulation, design, deployment, and then it can help also with verifying the test and integration of your radar system. Radar Toolbox, along with MATLAB Simulink and some other toolboxes, support 3 abstraction levels for radar lifecycle development. These levels include power level, measurement level, and waveform level. As we go from the power level to the waveform level, the fidelity of our design increases. And so the computational resources are also increasing. MATLAB and Simulink allows you to go from the power level to measurement level to waveform level seamlessly. And they have included here an example that shows that. Let's talk a bit more about what is power level and what are the other levels. The power level here, we are talking about radar link budget analysis that can be performed within MATLAB using the Radar Designer app. And the applications that radar engineer usually look for are the concept design and development, system analysis, and early stage phases or early phases development of radar system. Measurement level here, we are talking about detections. So the radar design here will output sort of detections that can be used for system analysis, scenario analysis, and for also designing and testing and tracking algorithms. If you would like to increase the fidelity of your design further, you can generate IQ signals from your radar design by modeling different components, including the RF circuits and the antenna of your radar. Modeling radar at this level will help you with designing and verifying the SP algorithms for radar and performing an end-to-end performance assessment of your design. Speaking a bit more about fidelity of or level of fidelities and how they increase the simulation time. So at the early trade or stages or at the early phases of your radar development, you would like to verify is your idea correct or not. So you don't need a very detailed model here. A model at the power level might be more than enough. I'm talking here about the radar budget analysis. This will help with verifying your ideas about radar that you are looking or you are aiming to design. Going further or moving further, you would like to have a detailed or more detailed design and understand if it will work in reality or not. And here we can say that we are talking about the measurement level. You generate some detections and you try your tracking algorithms on those detections. And then, like involving or including the impairments coming from the antenna and the RF circuits will help you with getting a more detailed design that mimics your radar system. And as I mentioned before, this will help you with testing and validating your radar signal processing algorithms. As it's shown on this chart, the fidelity or the level of fidelity increases, and so does the simulation time as well. So it's always a trade-off. The applications of Radar Toolbox with MATLAB and Simulink also include connecting to hardware and testing with them. It's always good to start with simulation, but sometimes it helps a lot and it validates our idea about radar signal processing algorithms or any other algorithms such as tracking algorithms or clustering algorithms. So in this case, we would like to acquire some data or signals from real-world radar systems. MATLAB Radar Toolbox help with accelerating radar development as it integrates seamlessly with hardware from different vendors, including Texas Instruments. MATLAB Radar Toolbox with Texas Instruments millimeter wave radar integrate in two different ways or two different workflows. If you are designing and testing some clustering and tracking algorithms, you can configure and acquire detections from the Texas Instruments millimeter wave radar directly to MATLAB and perform these tracking and clustering algorithms or any data analysis algorithms. The second workflow is about getting the IQ signal from this hardware. And that can be done using another board or a card. It's called TI DCA 1000 EVM. So in MATLAB, you're going to get the IQ signal. And this IQ signal can be used for radar signal processing algorithm testing and verification. I have linked here some examples for you to explore later on as we are going to share these slides along with the recording. Let's now dive deeper into Radar Toolbox. I've been speaking about the MATLAB and Simulink solution for radar design. And at the core of this solution, we have the Radar Toolbox. So with the Radar Toolbox, you can perform radar system engineering, radar scenario and data synthesis. You can also design multifunction and cognitive radars and integrate AI workflows into your design. With this application or with these capabilities, you can perform link budget analysis and evaluate design trade-off. You can simulate radar scenarios, and you can model multifunction radar, including their resource manager, can include and integrate AI workflows into radars and synthetic aperture radar so that you can radar capabilities. Let's now dive deeper into each of these applications and start with radar system engineering. The system parameters of a radar include fundamental radar parameters such as operating frequency and peak power, hardware specification such as noise figure, and beam shape loss. You can also consider the processing and scanning gain and losses in your budget analysis. And of course, you want to include the effects of targets and environments in your link budget analysis. and system design, such as targets, radar cross-section, and swirling models, as well as the surface cluster and precipitations. So these are the different parameters that are involved in radar budget analysis or radar equation analysis. And it has been always challenging to do a quick analysis of this radar equation, as it depends on many parameters. For that, Radar Toolbox or Radar Toolbox development team has came with this very nice app, very interactive app. It's called Radar Designer app that has 5 built-in configuration to help you with quick design and iteration over different configuration and parameters. It has a configuration for long-range surveillance radar, for airport radar, for automotive radar, and so on and so forth. These configurations were validated and tested with the probability and detection and related metrics table, as you can see here. And also you have different plotting methods so that you can test and verify and assess further your radar configuration budget analysis. Here I have a video that I included here to show you how to use this Radar Designer app to design an airport radar that meets 3 requirements: maximum detection range, unambiguous range, and the range resolution. So in this very short video, I'm showing how to meet the requirements of range resolution, but I have a longer version of this video that I'm happy to share afterward. So we first start with opening the Radar Designer app from the MATLAB apps tab, and then we open a new session. We can rename the radar configuration, and then the next step is to go through the different parameters of the radar. And we start with the main parameters, or let's say the fundamental parameters of radar design, including the frequency, the peak power, and the PRF. Not only that, you can also include the antenna scanning, detection and tracking parameters, and loss factors. Let me go further. So all these parameters that we mentioned before in the previous slide can be included in the radar budget analysis, so that you have a solid analysis of your radar configuration design. You can also include the environments impairments by changing the free space into false, and then specify different parameters for the Earth model, including the atmospheric model. The precipitation also can be modeled by changing it from none to fog, or maybe gas, or even clouds. It depends on the radar that you are designing. The next is to model the radar target, the target that you are trying to detect using your radar. And that can be modeled with specifying the radar cross-section, the swirling model, the elevation angle, and the max acceleration. Later on, you would like to set the metric and the max range constraints. Remember that we have 3 requirements, and one of them is the maximum detection range, and that's our max range constraint. So at the bottom of this app, you have a table, and this table tells you about the performance of your radar. It has different columns: the threshold, the objective, and also the column where you can see different colors. And you have also different plotting functions that help with assessing your radar performance. So what I'm going to do now, I'm going to just change a few parameters here so that I can meet the requirements for the range resolution. So the range resolution is handed. I want to change it to a value of 80 meters, and see if my radar will still be able to detect properly or not. So these colors here show that all these satisfied requirements are highlighted in green, but now the range resolution is highlighted in yellow, meaning that it's not fully satisfied. People like they are experts in radar, they know that changing the pulse bandwidth will help with improving the range resolution, and that's what I'm doing here. So I'm changing the range resolution, putting it to a higher value, and that will help with achieving this requirement, and it's now highlighted in green. So this is one case study or one use case of Radar Designer app is to assess the radar budgets against some requirements that's maybe shared by a stakeholder. The end of the workflow, or the last step of the workflow, is to export or to share your work with your team, or for you to do some afterward analysis. This report, this table can be exported as a metric report that will generate a script, and this script can be executed so that you get that report in a form of table. You can also export your analysis. I'm talking here about this plot as a MATLAB script. Another way to export is to export radar data generations or radar detection generations to MATLAB and use it so that you can move to a higher fidelity model, the ones that we spoke about before. So this was a quick overview of what you can do with a Radar Designer app. There are many other applications, many use cases that you can use Radar Designer app for, and remember, it's for power level analysis. So this analysis, or this radar equation analysis we have done, can be used later on to move from the power level to waveform level. And what you see here is a radar system architecture in System Composer, our model-based system engineering tool. Here we are designing a radar along with the different other components for the communication, command center, targets and environments, and so on and so forth. This is the abstraction level. This abstraction level can be decomposed further to include different components of radar sensor. And the requirements can be also imported to MATLAB using requirement toolbox and link it to different components. Later on, you can design the behavior of radar sensor. I'm talking here about the different components that I showed in the very first slide. The last step that you would like to do is to perform radar requirements-based testing using Simulink tests. And what you see here is the requirements editor showing that these requirements are linked to specific components, and they haven't been verified yet, but they are implemented. Let's now talk about how we can take this radar and test it in scenarios. To define and simulate radar scenarios, you have a very straightforward workflow in Radar Toolbox. You start with modeling platform and targets, and that includes modeling your targets using bounding box or using just a RCS signature. Then you model the environment, including the cluster from surface. If your radar is for, let's say, some ground for an airport, so in this case we're talking about land surface. If you are talking about a maritime radar, you would like to model the sea cluster, and you can also include or add the impairments coming from the atmosphere, and that include the effective Earth radius and diffractions. For the trajectory, you can use different ways that are available within Radar Toolbox to model the trajectories. You can use pneumatic properties, including the acceleration, velocity, and so on and so forth. The other way, or the higher fidelity way to model trajectories, is to use waypoints. And that includes position, orientation, time of arrival, ground speed, so on and so forth. Or you can even import terrain data and include it into your scenario. Sensors can be modeled, or radar sensor can be modeled at different levels, as I mentioned. For such a scenario, we verify or we design radar at measurement level using scenario analysis and tracking design. We can also design at a much detailed level, which is the waveform level. And that will include DSP algorithms, end-to-end performance assessment, and so on and so forth. So the last step here is to, put your scenario and along with the sensor in a while loop and iterate over different scenarios to generate IQ signals, detections, and tracks. And to stress out more your design, you can perform some sorts of Monte Carlo simulation to perturbate the ground truth and sensor to increase testing and robustness. Let's speak a bit more about different steps of this workflow. You can model radar targets with different levels of fidelity. The first level of fidelity is the points. You can just model it with the RCS value. And what you see here is the RCS analysis that you can do with Untitled Toolbox. You can also model your target with the actual shape and perform the analysis based on that shape. And you have different functions and functionalities available under Radar Toolbox to do that. Another way to model targets at higher level of fidelity is multi-scatterers, and that will help with capturing more details about your targets. The much higher fidelity of platform and target modeling, or let's say target modeling, is the meshing. You can import your design that you have in any other third-party software and do the analysis using electromagnetic solver within MATLAB and Simulink. Coming to the model environments, there are different ways to model it. It depends again on the radar that you're designing. If your radar is for land applications, you are here likely to go with land surface cluster modeling. And for that, you can import terrain data using mapping toolbox and visualize this. You can put it within your scenario that includes your radar sensor that we're going to talk about in a moment. And this is an example that I linked here showing a scenario, or radar scenario that was designed, including the radar beam and the patches. Here it tells you about the radar performance in this terrain. The atmospheric reflection can be also modeled, and we have a set of built-in atmosphere models or atmospheric models based on effective Earth radius and refraction. There are three options that you can use to define the land elevation. You can model a flat surface, you can use digital terrain data, or you can also include a custom terrain that you can import to your MATLAB and Simulink projects. Also, you can use a custom model, and this table shows you different models that can be used with Radar Toolbox. For modeling sea surface cluster, there are different built-in models. I will here mention the Al-Fuhaili model, which is based on a multiplication of spectral model and spreading function. And this will give you the sea motion model. The Al-Fuhaili model is based on different parameters, including direction, speed, fetch, and so on and so forth. This is the most and the very commonly used one for sea surface cluster modeling. For modeling the trajectories, as I mentioned before, you can do the different ways, or you can do that in a different ways. You can model the automatic banking if your radar is mounted on an aircraft and it's landing. You can model different phenomena. You can also model the automatic pitch and rule to conserve momentum. And this example shows that for a quadcopter. Modeling the sensors, this is something we spoke about many times. You can model sensors in different ways and at different level of fidelity. You can generate detections and use them for testing and tracking algorithms, finding the moving direction. You can use those detections later on for tracking algorithms testing and validation, or you can also do that for clustering if you would like to group your detections. The other level or the other way to model the radar sensor is the physics-based radar transceiver model, where you include different impairments and different parameters of the radar design or the radar system, including the waveform, the antenna, the RF chain, and so on and so forth. And this will help you with getting a high fidelity model of your radar design that will help actually with verifying further your different algorithms. And for visualizing the output or the results of radar, the output of radar DSP block, you can use different ways available within the Radar Toolbox, including the range time, range Doppler, angle Doppler, and so on and so forth. And whatever is shown here in a different color means that those are detections that you can apply a CFAR to find. This is an example showing how to define a scenario with a terrain data for simulating an airborne radar or radar altimeter. This is actually the scenario. We have an aircraft that is landing or about to land, and we have a radar mounted on it. What you see here is the beam. This is the scanning beam, or this is what the radar can see, and this is the altitude. So this radar will help us with finding this information, or will help us with reading the altitude. In MATLAB, you can do it this way. You can simulate it. You can, import the digital terrain data into MATLAB and put it within your radar scenario. And what is shown here is exactly what I explained before in this image. Another way is to import real-world digital terrain data instead of this, let's say, 3D dummy scenario. So you can import the real-world digital terrain data and include it. So this is a radar mounted on a aircraft that is trying to land, and whatever these dots shown here are the detections. Speaking a bit more about the waveform, here we are using a triangular chirp or triangular waveform with an up sweep and down sweep that will help us with better reading or measuring the altitude. The antenna has a directional beam, and that's what we actually need for this application. It's also showing different frequencies, or it's showing the antenna performance in a azimuth cut. So here we can also show the 3D pattern of the antenna instead of this azimuth, and while the elevation here is just 0. So this is something I'm happy to follow up on and explore how we can design an antenna and analyze it in 3D manner. Now we would like to assess the performance of our radar signal processing algorithms. So the radar signal processing algorithms are mainly based on first acquiring the RF signal, and for an FMCW we have a mixer. After that we filter out that signal so that we get rid of high frequencies, and we perform a FFT chain or FFT processing to get the range response. Because we have a triangular waveform here, we are looking at two different range response, one for the up sweep and the other one for the down sweep. Combining the information from these two, we can get a better radar detection performance. Now that we have the range response, we can apply a CFAR detector or a adaptive detector. The very famous one is this CFAR, or cell averaging constant alarm algorithm. The other way to assess or to evaluate your radar performance is to look at this map. And you can see that we have different regions. The gray region showing that if the detections are in the green region, meaning that our radar is performing well, and we are happy, or we are okay to go to the other steps of the workflow. Maybe deploy these radar signal processing algorithms to an embedded system. If the detections are outside of this, we can still accept to have detections in this shadow yellow color here. But if they are outside here or there, then in this case we need to go back to our design and improve it further so that we get the correct configuration of our radar design. Now let's see how we can design a multifunction and cognitive radar and integrate AI applications or AI workflows into them. First, let me just tell you a bit about what is a multifunction radar. So far, we have been talking about traditional radar, a radar that can detect, a radar that can search, track, classify, communicate. So these radars are usually separate. Radar engineers came with the idea of combining all different tasks, and they came up with this multifunctional radar aspects or concepts. A multifunctional radar is a radar that can perform multiple tasks in the meantime. And hence, we need a resource manager. And that's why every time you see a multifunctional radar, it will have a resource manager block. A multifunctional radar or multifunction phased array radar can help with different functionalities. It has the electronic scanning, so the antenna is fixed, but we are creating different beams electronically by changing or shifting the phase. We can control parameters, and those parameters can be used for resource management. It allows to do or to perform many tasks supporting different functions, and these functions can be multiplexed in time and angle. And so every good thing comes with some challenges and constraints, and that include multifunctional radar. So these constraints are related to resources. And when we say resources, we are talking here about the bandwidth, the computations, and the emissions. One more thing about this specific type of multifunctional radar is that it sends or it has different beams, and these beams will do different tasks, as you can see on this slide. And the multifunctional radar are usually a closed loop. I mean, to simulate them, you need to close the loop and see how your resource manager is going to handle different tasks. This is an example showing the closed loop of a multifunction phased array radar. And this multifunction radar is going to do 3 tasks here: search for volumes and also the queued search. The third task here is the tracking. So once the radar or the task of looking for those targets is done, we would like to track those targets, right? And hence we need to always talk to the scheduler or the resource manager, the radar. These detections or this scenario can be modeled also within MATLAB and put that radar sensor, that multifunctional radar sensor, in a scenario so that you can verify further the performance of your radar. And this example shows the resource management for 6 targets. So whatever is shown here in these squares are targets, and we have 6 targets. And remember that we said this radar or this multifunction radar has to do or to perform 3 tasks: the volume search, the keyword search, and then the tracking. And then on the other side, we need to look at the resource manager and see how it's handling different tasks. With MATLAB and Radar Toolbox, you can visualize different resource manager resource constraints, including the bandwidth, the power aperture product, and the time fraction. The colors here mean the resource that were allocated to specific tasks. We can put this resource manager or this resource management block under stress. So we would like to increase the false detections and see how our resource management is gonna behave. So as you can see on the resource management block or plot, now it's different. It shows few abrupt changes, meaning that it tries to allocate resources to specific tasks when it is needed. And this multifunction radar can become smarter and learn from the environment, from their environment. Meaning that a radar can adapt to its environment by changing few parameters or maybe switching between different waveforms or even steering the beam toward a specific area. One of the key or the techniques is parameters agility that can improve the detection or the detectability of your radar. And that includes both repetition frequency agility, waveform agility, and then we have the beam steering as well. These examples that are available under or shipped with MATLAB and Simulink and some other toolboxes shows the integration of these different techniques into multifunction radar. So you can use the pulse repetition frequency or change it or adjust it based on the environment detections to simulate how your radar going to behave and how it's going to be able to detect with different PRFs. So some targets will be detected only if the pulse repetition frequency is high. Some others are okay, can be detected with a low pulse repetition frequency. And this model is available in Simulink. Is the frequency agility for interference mitigation. Aerospace and defense, we always have the jamming signals coming from other radar or coming from spoofing systems. And we would like to make our radar smart so that it can detect and mitigate this interference or these jamming signals. A technique that can be used for that is to change or to adjust the frequency based on the previous detections of radar. So you can use a switch, which is a block available in Simulink to switch between different frequency bands and see how that's going to be reflected or see how that's going to affect in your detections. So what you see here are two signals or two spikes. One is for our real reflection, and the other one is for the spoofing signal that we would like to mitigate. After applying or changing and switching between different frequency bands, you can see that we were able to filter the spoofing signal. Yeah, sometimes we'll lose the target as well, but that's because the target maybe is outside of the range of the radar. And the trend that's happening in all the application is the integration of AI into different systems. And that applies also to radars. You can make your radar smarter enough to learn how to classify targets, how to mitigate interference, and so on and so forth using deep learning and machine learning algorithms. Our artificial intelligence workflow starts with creating and accessing datasets, pre-processing and transforming data, and then building predictive models, and eventually you would like to accelerate the training and deploy to production. For radar applications, you can create a data store using functions that are available within MATLAB. You can simulate and generate synthetic data, and you can also label your signals interactively using apps such as Signal Labeler. For the pre-processing, different features and functions are available for you, and they are all supporting the low code, no code features. So instead of writing a lot of code to do, for example, the signal transformation from a time series to a spectrum, you have got one function or even an app to help you with that. For feature extractions, you have apps and functions, live tasks to help you with that as well. And this will help you with extracting features and preparing them for the model. The model can be also designed interactively using Deep Neural Network Designer app, or you can also use apps such as the classification learner and regression learner that are available within some specialized toolboxes to design these models. The acceleration can be done with the parallel computing features, and you can also scale up to clusters and clouds. The last phase or the last step of the workflow is to deploy. And there are different ways to deploy. You can generate or you can create and generate an app that can be installed on desktops or even deployed to the web, and they don't require MATLAB license in this case. You can also deploy to an enterprise system or generate C, C++ code. The other way is to embed into devices, hardware from different vendors. And for that, you have got the embedded coding features or embedded coder that can help with generating a optimized code for that specific hardware. An example that I would like to mention here about using AI for radar application is maritime cluster suppression with deep learning networks. I mentioned in the very beginning that clusters are very challenging to deal with. And we have got algorithms, let's say traditional algorithms such as CFR, MTI. These algorithms can help with suppressing or mitigating this cluster. But we always have false detections. And so why don't we use the AI features in this case? We can use deep neural networks to suppress clusters coming from sea or from the sea surface. This model shows how to design that in Simulink, in MATLAB and Simulink, a scenario using Radar Toolbox features, and then collecting the data and prepare it for training. And the scenario included variables for the surface, target, and so on and so forth. So you are ending up with this, I believe these are spectrums of your radar reflections from cluster and target. And then we would like to get only the targets. So deep neural networks can help with that. So feeding a neural network that we can design using Deep Neural Network Designer app with this training data, we can train a model that help with, suppressing the cluster or mitigating the cluster and keep only the targets. And that's what we see here as output. So key takeaways from this talk. With Radar Toolbox, along with some specialized toolboxes, you can perform link budget analysis and evaluate design trade-off at different level of fidelity. You can simulate a radar scenario to generate synthetic data. You can model and simulate resource management for multifunction radar. And also you can integrate AI capabilities into radar application to make them smarter and reliable. call to actions. So where you can get started with Radar Toolbox and the other involved toolboxes. Radar Toolbox has more than 100 examples and cross products workflows. So I have listed here a couple of them. For radar system engineering, you have got many examples that show you how to do the radar budget analysis and then link them to requirements and do some, let's say, advanced analysis. You can also use Radar Toolbox for radar the scenario design and for generating data, radar data. And you have examples to get started with. So these are some sorts of reference examples that I recommend to everybody to use as a reference and customize them. For multifunction and cognitive radar, there are many other examples. And AI for radar as well, including the application of AI for SAR target classification using neural network, or also labeling signals ahead of feeding them into a neural network mode. More examples can be found on the Radar Toolbox documentation page, and I highly recommend that you check it just after this webinar. Thank you so much for attending this session.